Hey Year 12s, nice to see you all. Thanks for coming, guys. Okay, so I'm gonna go straight into my lesson today because we don't have an awful lot of time. Should only take 30 minutes or so, I hope. Right, and then what I like to do is I like to then go to my notes and then disable my camera, because if I do that, it means I get a bit more performance. So let's just go with that. Disable. Don't crash. Winner. Right. So today's lesson, guys. So next, I'm going to set you your homework. So today's lesson is on measuring enthalpy changes. So the first thing I want to do is just quickly recall with you guys. I'm going to flip my tape of my tablet over into write mode. So recall internal and external calorimetry. So in order to measure, we know that reactions produce heat energy changes. Yeah, we know that they can either be endothermic or exothermic. And we need to be able to understand how we measure it practically. And calorimetry, I'm just going to highlight this word. Calorimetry is a practical subject. Yeah, practical to measure heat energy change. Notice I never say the word heat or energy separately. Heat energy change. Yeah, and you'll remember this. You did it at GCSE. Yeah. The next thing is I want to discuss why some enthalpies are hard to measure. Not just hard, some of them are simply not possible. And I want to give you some reasoning behind that, and I want to chat to you about Hess's law. Okay, so the first thing I want to do today is chat to you about internal and external calorimetry. So this is going back to GCSE. So at GCSE, you guys learned two practicals for measuring heat changes. Two methods, GCSE, two methods to measure enthalpy changes. Now, by the way, they used to be called internal and external. Now, these terms are kind of dead now. They don't call them that anymore. I don't know why they decided to get rid of it. I preferred it. It always made more sense to me when it had those words in it. Now they just go, oh, it's just calorimetry. It does annoy me. So the external calorimetry, so external calorimetry, what this is, external simply means, and I'm going to put this in red, and I'm going to star this. So the word external, yeah, what's this talking about? So external is that the reaction producing heat or absorbing heat energy is outside of the water. I'm just going to put outside the water. This will make more sense when you see the diagram. So the example of this, of course, is the enthalpy of combustion. Delta HC, the enthalpy of combustion, the heat energy change when 1 mole of a compound is completely burnt in excess oxygen to form CO2 and water only, all under standard conditions and in standard states. Yeah, so for example, now we can do ethanol. Let's do ethanol. CH3CH2OH plus O2, and I'm going to make CO2 and water, H2O, and standard states. Ethanol is a liquid. Oxygen is a gas. CO2 is a gas, and water is a liquid. Can I just point out, by the way, that this is immediately lends itself to a problem. I'm going to balance the equation, by the way, 2 carbons, hydrogens, 6 hydrogens, oxygens, 4, 3, 7. We've got 1 there, so I can put a 3 there, and I'm done. So this equation here is the standard enthalpy of combustion. We cannot do that practically. The reason being is the water, of course, is going to come out in reality. So problem is that H2O in reality will be left as a gas. So it doesn't fit perfectly. We can measure it, and it's easy to measure, but it's not going to be particularly accurate measurement. And what does external calorimetry look like? It looks like this, and yes, you have to be able to draw it. So you have a copper calorimeter. So this is actually called a calorimeter, and this is literally a beaker. Yeah, it's a beaker or / metal pot. Now, just to tell you that the metal pot is better because it conducts heat better, but it then also has a higher heat capacity as well, which is a bit of a nightmare. But we're going to then fill it with water. So we've got our H2O here, and the H2O, of course, is in the form of a liquid. And what we then do, we then have our little burner. Yeah, we have our little burner. And our burner, yeah, contains, that's a terrible burner, I'm so sorry. And this has a wick in it. And the burner contains ethanol. Yeah, so this burner contains our fuel. And what we do is we burn this, yeah, in order to be able to measure its heat change. Yeah, and this is internal calorimetry. Yeah, sorry, damn it, this is external calorimetry, because the heat source, the source of heat energy, is outside the water we're using to capture. Yeah, heat energy outside the water. So what's happening now, by the way, this has a massive problem, because what we're trying to do is we're trying to capture the heat energy in the water to be able to measure the total heat output. But external calorimetry is incredibly poor. It's a terrible practical because the heat loss to the environment is huge. Heat loss is massive. Yeah, heat loss is massive. Number one problem. Yeah, other problems, the water isn't being produced in its standard state, so we're not going to get an accurate figure. Second reason is the copper is going to have a different heat capacity, meaning the C value we're going to use is not going to be accurate. And the other one is incomplete combustion of the fuel plus evaporation of the fuel and the water. This is a nightmare practical. It basically is just a pile of garbage. So this is external calorimetry. And you did this at GCSE. Yeah, and we can talk about that method later on, but I just want to kind of do a bit of a summary today. So then there's internal calorimetry. So internal calorimetry is when the heat source is inside the water. Yeah, reaction producing heat energy or absorbing it, either one, producing stroke absorbing heat energy. Absorbing heat energy is is inside the water. So these are most of the time reactions in solutions. And the practical is very different. The practical now looks like this. You now have a polystyrene cup. Everyone remembers this from GCSE. You've got a polystyrene cup, which is usually put inside a beaker. Yeah, we can label all this as well. So this here is a polystyrene cup, a terribly drawn polystyrene cup. Polystyrene cup, and this is to act as insulation. Then it's going to be sitting in a beaker, and the beaker, of course, provides a second layer of insulation, but also it provides it with some weight so it doesn't fall over. The reaction mixture is here, and we add our thermometer. Suddenly realized I forgot my thermometer in my diagram of external. There we go. Thermometer. There we go. Thermometer as well. Now this one is far better because the heat loss is massively reduced. Yeah, because what's going to happen if, let's say we do HCl reacting with sodium hydride, let's do with HCl with calcium carbonate. Yeah, CaCO3. Well, that reaction now, because the heat energy of the reaction is inside the water, it's much better in terms of far less heat loss because it's already inside the water. So it's far better, much less heat loss. So this one isn't there. By the way, there's actually a further kicker with this because we can actually use a graph here, and I'll do this in a later lesson. We can use a graph to actually take into account heat loss. That's a nota bene, that, see later notes. Nota bene, I'm going to do the nota bene in red. Yeah, nota bene. This is much better since we can use a extrapolated graph to account for heat loss. Amazing. Don't get me wrong, guys. I don't need you to remember that quite yet because I'm going to explain that more when I'm going through these in more detail anyway. But you did this. By the way, that's A-level. The rest of it's just GCSE. Yeah, but you did both of these methods at GCSE and you evaluated the pros and cons in them. So it's nice just to recall that these two still stand at A-level, and we would be doing these in lesson and discussing all the problems with them. Now what we want to do is we want to talk about some reactions that we can't measure. So, okay. So some reactions, let's just do a title. Reactions, subtitle. Reactions that can't be measured or difficult to measure. Can't be measured. So now the first one, which is a very important one for Edexcel. So everyone here remembers their test for water, don't they? This would be where it'd be nice to have someone pop up on the YouTube chat, which I've lost, which is amazing. Somebody on the chat to say that they remember their test for water. So the test for water is anhydrous copper sulfate. I'll do anhydrous copper sulfate. And this is nice for us to do a bit of a recap on this. Perfect. So anhydrous copper sulfate is the white one. So we can do test for water, bullet point. Test for water is anhydrous copper sulfate. Now, anhydrous copper sulfate is white. Now, when you add water, add H2O, yeah, we get a very clear observation. Observation, French for observation. It goes from white to blue. White to blue. Now, can I just point out that Edexcel like you to know another one, an alternative to this? The alternative test for water is anhydrous alternative. You won't have seen this one at GCSE. Alternative is anhydrous cobalt chloride. Cobalt chloride. Add water, and by the way, that color of that guy is blue. Is blue. And then you add water, add H2O, and the observation is it turns pink. Observation. Blue to pink. Blue to pink. There we go. So, but what I'm trying to, this actually isn't really, this is just me doing some chemical tests with you and roping it into the lesson, which is always nice. But in reality, what I want to talk to you about, so if I have, and this is what I would demo in class, I would get a whole load of solid copper 2 sulfate. Solid. And this is white, and it is anhydrous. Yeah, anhydrous. What I would then also show you, hydrated copper sulfate. And hydrated copper sulfate, which you also need to know, is CuSO4.5H2O, and that also is a solid. This is blue, and it is said to be hydrated copper sulfate. Copper 2 sulfate, if you like, Roman numeral. So, now, this is the image you've got here. They are both solids. This is important. Nice, have a look on the chat. Copper sulfate, white to blue. Thank you, Sian. The pink one, nicely done. So this here is what it looks like. And notice that they are both solids. Now, the hydrated one has water trapped inside the crystals. Now, here's the thing. If I wanted to convert anhydrous copper sulfate into, I'm going to add 5 waters, and I'm going to form hydrated copper sulfate. Can anyone guess what the problem is in that practical? In reality, that isn't going to happen. Not at all. Would someone like to guess what part of the equation is incorrect? This is where I need my chat up again, and I've lost it. There we go. It is there. It just takes us so long. The delay is massive. Now, the problem here, guys, is that if you add anhydrous copper sulfate to water, yeah, this is liquid water, standard state. The problem is it's not going to form a solid. This will not happen. That direction of the reaction will not take place. I'm not going to make a solid if I add water to copper sulfate. No, this will not happen. What will happen is that I am simply going to form Cu2 plus aqueous plus SO4 2 minus aqueous and 5 waters. What it's going to do is it is simply going to dissolve. That's all it's going to do. It's going to follow this path. It will dissolve. It will dissolve to form a solution. What that means is you cannot measure this reaction directly. This reaction here, delta H1, that reaction there is not possible to be measured directly. We have to measure it indirectly. Let's have a look at other reactions which would be very difficult to do. Let's look at some other ones. So another great example, e.g. number 2. I've suddenly realized my writing's just suddenly got massive, hasn't it? I don't really want that to happen. I want to try and stick with even-sized texts. I tend to have a habit of things just getting larger. So there we go, we've got e.g. number 2. Let's have a look at this one. So this one, let's do best one here to do. Oh yeah, so this one, ethene plus oxygen. If I take ethene plus oxygen, both gases, and I react them together, I want to form what's called epoxy ethane. I want to form this guy. Can I just point out that this reaction is this is a very famous reaction. This is epoxy ethane. Isn't that cool? A long lost family, the epoxies. If anybody's interested what epoxy resin is, it's got that structure in it. Yeah, they're very unstable. It wants to break apart very easily. Yeah, so this is an epoxy. Now that reaction, this reaction cannot be measured. Yeah, that will not happen. It's very, very difficult to get that reaction to happen, because what's simply going to happen instead is it's going to combust. I'm going to form CO2 and water. If I take ethene and react it with pure oxygen, it's gonna burn. Like, it will. Madness to think it'll do anything else. Yep, this is the reaction that will happen. It'll just go through combustion. So, once again, very, very difficult to measure it directly, because some of it will combust. It's an absolute nightmare when they're trying to make this stuff. They can be done. They use all kinds of cool catalysts to do it. Silver is actually the catalyst for that particular reaction. Anyway, so once again, can't be measured because it'll prefer to go through combustion than to form the organic product we wanted. Let's do one more as well. Number 3. So the next one is let's take ethane. And what we want to do is we want to take ethane and we want to burn it, but we want to burn it to produce carbon monoxide. Yeah, so I'm going to burn this incompletely. So 2 carbons hydrogens, oxygens, 5, 2.5. Right, I want to do that. This reaction will be borderline impossible to measure. That reaction won't happen because the problem is we're going to get a mixture of reactions. Yeah, we know that we're going to get carbon plus water as one reaction. We're also going to get a bit of carbon monoxide and water, another, but we're also going to get some complete combustion as well. We always end up with a mixture of 3 different reactions when you burn anything. Getting complete is easier because if we use excess oxygen, most of the time you'll get complete combustion. So that one's easier to measure, but these two, really tough because the problem is you're going to have a mixture of outputs, which means I can't measure them directly. Another great example of that one, another great example of multiple products being produced. Let's say I want to take pentane and I want to crack it. You remember doing cracking at GCSE? Yeah, I'm going to take pentane, I'm going to heat it in the absence of air over a zeolite catalyst or aluminium silicate catalyst, and I'm going to crack it to form ethene and propane. Yeah, I'm going to crack it to form these two. Well, in reality, I'm going to have a mixture of products. I may get that reaction. Trying to measure that directly is impossible because what's going to happen is that reaction won't be possible because I'm going to have another product as well being propene and ethane. I'm going to get a mixture of products. This is a nightmare. Yeah, because I'm going to get a mixture of this one and a mixture of this product as well. So we realize that some reactions just are very difficult, and I will include this on the homework so you guys can try and start to wrap your head around the odd questions that Edexcel asks, and they usually simply tell you that it's not really possible and they ask you to try and explain it. And so it'll be good to have a look at some exam questions with that. So I've done my second learning objective today. I'm going to end my lesson here and I'll introduce Hess's law next lesson. But I will set you a homework. In the homework will cover our first energetics lesson, where I will give you some energetic definitions from exam papers and some equations and some multiple choice. And I'll also then give you some questions regarding reactions that cannot be measured, again, from exam papers. I will leave it there for today. I'll turn my camera back on. There we go. Excellent. And I will leave it and go start cam. Get rid of that one. Right, guys, I will leave you guys be today. I hope you guys have a nice rest of your day. And as I said, I'll set the homework on the class shortly.